So welcome to this lecture series on exploration strategies, and in this video we will actually start with a small motivational part and an introduction of a formal framework called the multi-armed bandits that will serve actually as a formal background that we will use throughout this video series. So that's a little bit of an agenda that you will see in this video series. So in this video, we'll actually take a little bit look into a motivation and problem definition of exploration, and we will actually end with the definition of multi-armed bandits and the formalization of the so-called regret that we will actually use in the upcoming videos to actually benchmark our exploration strategies. In the next video, we will actually talk about classic exploration strategies. Some of them you're already familiar with. The easiest one basically is the epsilon greedy algorithm. This is actually what we introduced early in this lecture too. However, there is some more advanced techniques to actually guide the exploration process, namely Bayesian or non-Bayesian upper confidence bounds or Thompson sampling. In another video, we'll actually then in a much larger part of this lecture series, we will actually talk about exploration and deep reinforcement learning. We will actually do this in three parts. The first one is the count-based exploration techniques. The second part is the prediction-based exploration techniques. And the third one is the memory-based exploration techniques. And we'll end this lecture series with a small summary and outlook on this topic. Okay, so let's get started with a general motivation and problem definition first. So while we actually motivated the problem of exploration early in the lecture already, our aim in this series is actually to dig into the problem of exploration a little bit more theoretically. And at this point, I also find it interesting actually to motivate the exploration problem through motivational examples that you know from the real world. So a very famous example, a very popular example that might every one of you already be familiar with is the selection of a restaurant. So just imagine that you move in a new city and you try out different locations. You go for an Italian restaurant or you go for a Croatian restaurant. And if you want to exploit your knowledge, actually what you would do is you would always go to your favorite restaurant. So this is actually the usual place you always go to, and there is a grand opening. And if you want to explore, you might try something new. Meaning that you take some risk actually to explore the state space in a sense and explore some new restaurants in order to get new experience. Another well-known example is the problem of oil drilling. So if you are like an oil industry company that you might like dig for oil in the northern seas, if you want to exploit your knowledge on how oil is actually distributed over the sea, you want to drill at the best known location that you will be knowing. However, if you want to explore a little bit and find maybe new locations, you want to drill at a new location actually to make some testings and evaluation if there is something to find over there. So you might either find nothing or you might find millions of barrels of oil that make you really, really rich. Another very nice example that's also maybe the problem of exploration, a very classic exploration problem that has been studied a lot, is the problem of online ad placement. So the question is, if you go to the internet, and the question is from a provider point of view, which advertisements to show to you. So if you want to exploit your knowledge about your current user, actually you will show him the most successful ads, or the most those ads that are actually very close to what you used to be what you're used to saying being successful for that user and customer. However, if you stick always to your knowledge, you will never be actually knowing. You want to actually know what the user is going to like, and in order to actually get some information on that, you actually have to show him different random ads in order to gain some knowledge if he's liking it or not. And I mean, those ads he can either be totally irrelevant to the customer, or eventually maybe the customer will even click on these ads. So this is a classic exploration problem that you also know from real life. So actually now if we talk about reinforcement learning, how did we actually tackle the problem of exploration in RL so far? We have seen actually in early parts of the lecture when we introduced model-free control, so we actually moved from model-free prediction to model-free control, and it turns out that if we want to come up with an improved policy, we actually find out there's a problem with exploration. So whenever we just improve our policy with the argmax operator over our Q function, we have seen that this can pose problems for bootstrapping the Q function, as we actually never really explore the really good actions that we can take in the state space. In order to actually tackle this problem a little bit, we introduced the epsilon greedy policy improvement. And in the epsilon greedy policy improvement, if you remember, there is an epsilon chance that you actually do not exploit your current knowledge, but you will take some random action that is not your argmax action in order to gain some knowledge on the state space. It might actually give you some bad rewards in it. However, you will gain some knowledge about how the world actually behaves. So actually what we did is we occasionally tried something that we think has been or would be suboptimal in order to find out if it is really suboptimal. And I mean, if you have tried during the implementation of the DQNs, for instance, if you have tried implementing working with like in here, like Atari, you will see that, or if you look in the internet, you will see that some of these games of the Atari domain are really easily solvable with epsilon greedy. So there is no real thing to really think about it further, because actually playing breakout or playing Pong using epsilon greedy is a really nice thing. A nice thing to do that actually works well in practice. The same applies also to Choco Hopper environment. If you go for epsilon greedy in here, you will see that they are actually working pretty well with the methods you already have learned. However, I mean, if you just select a different environment, for instance from the Atari domain, you will actually encounter the problem that epsilon greedy exploration not always works that well for all of the games. So there is a number of games actually where epsilon greedy is a perfect way to go. However, epsilon greedy exploration does not work on a subset of these games that are actually called hard exploration games. So within Atari 2600, there is a known number of games that are called the so-called hard exploration problems. And here are actually 4 of them. One of them is Montezuma's Revenge, here Private Eye, Sequest, and Pitfall. I actually don't know most of those games. I only know in Sequest that you actually have to shoot fish. However, you always have, from time to time, go to the upper side in order to get some oxygen. If you do not do this, you will eventually die. And however, Montezuma's Revenge is a game that is really that really serves as a kind of baseline in exploration strategies research in DeepRL. So, however, the question is, why are those games so much different than the others? Because, I mean, it is not necessarily that the game is somehow harder or the task is harder. So in Montezuma's Revenge, the goal is just, actually in this case, I mean, if you see this, the goal is actually to grab the key and to go with the key towards the middle point. And actually, maybe there is a skull, you may want to avoid this, to touch the skull. So actually Montezuma's Revenge in general is not that hard. You can go left, right, you can go up and down over these ladders here, and you take the key and go through the door. However, I mean, if you also look at this, so if you remember the brick shot in Breakout, this is maybe something that is really harder to find out than in Montezuma's Revenge. However, the question is why it is so much harder for an RL agent to play Montezuma's Revenge over Pong and Breakout. And it turns out that the reward structure is really complicated, or it does not really correlate. So actually, in Montezuma's Revenge, your actual goal is actually to get the key to open a door and then getting a reward. You will actually traverse different rooms in here. So we actually grab the key and you go on and you avoid the skull, and here you go over and you go here. And if you are at this point having the key, you will actually enter a door towards a new room. And the problem actually behind it is the reward structure of the game. So if you get the key, you get actually a reward, and if you open the door, I think you get a reward too. However, if you get killed by the skull, just nothing happens. So you use a life, so actually you start over again, but you do not get a positive or negative reward. It's just starting over again. And this kind of reward structure actually doesn't really or only correlates very weakly with the dynamics. So the game finishing conditions actually only weakly correlate with the structure, with the reward structure of the game. And this is actually problematic for DeepRL agent, because in contrast to us humans, we actually know that getting a key is something. It's somehow connected to something good, and we also know that there's a skull. A skull is usually nothing really good, so we actually want to touch it. So this is actually concepts that we as humans always know. However, the RL agent has simply to try out, and the only way of trying it out is just trying it and using the reward structure of the game to get some feedback. And however, this is maybe not so easy depending on the reward structure of the game. In other words, the reward structure doesn't really guide our agent in how the behavior emerges, and that is actually basically the problem of exploration and reinforcement learning. So actually this is, from a technical point of view, a little bit the motivation, what's the problem of exploration in DeepRL, and however, I can spoiler you a little bit, there is a solution to this problem. Okay, while we actually begin with using, so what you see here is the progress of Montezuma's Revenge in terms of game score, and what you see is here, the things that we actually saw so far in here, they are really somewhere between the low end of what you can actually reach in Montezuma's Revenge. However, we will also find, and we will also see methods and algorithms during this lecture where you can actually really outperform an average human player in the game of Montezuma's Revenge, which is a really hard exploration game. Okay, in order to grab the problem maybe a little bit, so now we motivated it over the RL environments that we can actually understand the problem, but how can we actually maybe formalize the exploration problem a little bit? And it actually turns out that, I borrowed this from Sergey Levine's lecture, there's actually two potential definitions, and both of them are actually correct. So the first one would say, how can an agent discover high rewarding strategies that require a temporally extended sequence of complex behaviors that for individually are not rewarding? So this is actually always the problem. We have to go and select actions for a long time without getting a positive feedback, maybe even getting a negative feedback, in order to get some real treasure at the end. And another way of actually defining the exploration problem is also, how can an agent decide whether to attempt new behaviors, so to say, discover ones with a higher reward, or to continue to do the best thing it knows so far. So actually, how can we actually trade the exploitation over the exploration? And actually, if you look a little bit closer about the definition 1 and 2, they seem they seem different, but actually under the hood, it's actually the same problem, because actually both definitions stem from the same problem. So there's the exploration issue, which means we should do things that we haven't done before in the hopes of getting a higher reward, of course. So we want to increase our knowledge, and in exploitation, we want to do what we actually know to yield the highest reward in order to maximize the performance based on our knowledge. So it turns out that exploration and exploitation, they are not really completely disjoint. So actually there might also be the fact that we want to exploit our current knowledge. So if you consider Montezuma's Revenge, we, for instance, have solved the first room and we get to the second room. And in order to gain now more knowledge, we have to exploit our knowledge for a certain sequence. So the sequence of getting the key and trying to get the door in the room number 1 in order to explore in the second room. So actually exploration and exploitation are not really disjoint, they are really actually tightly coupled. So it could also be, in order to explore at the right position, we have to really exploit information that we have in early states of the sequence, and then explore when we want to know more about the environment. Okay. And the question is now, what's the problem? What's the problem behind it? So actually, the dilemma that we are in is actually, the dilemma comes from incomplete information. So if you take like a theoretic view on this, we simply do not have all the information we would need actually, to solve everything. Which means that we need to gather enough information to make best overall definitions while keeping the risk under control to do something that's really catastrophic or worse. And with exploitation, we actually take advantage of the best option we know. And with exploration, we take the risk to learn about unknown options. And the question is always, how much risk can we take and how much advantage do we want to lose? And of course, something that you might also know, or what you might agree with, the best long-term strategy may also involve short-term sacrifices. Okay, so I think now I got it. I think you got it now. I told you much from different perspectives. So exploration can be very hard. However, at the end of the day, we want to solve exploration, actually, or we want to actually tackle the exploration problem as best as we can. And the question is, at the end, how can we actually come up with an optimal exploration strategy? So if you now ask this question, the next question would be, from a mathematical point of view, what does optimal even mean? So what is an optimal exploration strategy? And it turns out that it is from the online learning community, there's a term called regret to actually express what this means. However, we will talk about this in 3 slides. From a theoretical point of view, in order to come up with an optimal strategy, we first have to study how tractable exploration problems in MDPs actually are. This is also borrowed from Sager-Levine, and it's really nice because it really a little bit shows, it gives you an intuition about the complexity of an exploration problem. So in this lecture we will talk about, so this is actually also what we will be talking about a little bit in this video series. So we will start with multi-armed bandits, because actually multi-armed bandits, they actually assume small MDPs. However, it's very restricted MDPs. There is actually no states. We actually have only actions, and we only decide on the actions. So it's the most theoretical problem we can come up with, and it's also very easy. It's a one-step stateless RL problem. And actually what this is really nice with them is that they are completely theoretically tractable, and we can evaluate our strategies in terms of the regret versus a base optimal agent, which I will also tell you in a minute what this is. So if you now, on the other side, actually what you have is you have large infinite MDPs, maybe that stem from a continuous state space, as we actually saw them in the Mochoko examples or in complex robotic tasks. So on their side, usually this is where we are when we do deep reinforcement learning. We have no chance in theoretically making those things tractable. We cannot do much about theory in here. However, we can actually our goal is always to draw findings in here and actually apply them to deep RL and hope to work there as well. And in between, there's 2 more steps. So we have contextual bandits, which is basically similar to a multi-armed bandits. However, we have states in here. However, the actions do not affect the states. So we might have the context of you as a person in the ad placement. So you have certain preferences, and this is the state. And we evaluate the actions to take. However, your preferences wouldn't change. Okay, so actually we present actions in order to know more about your preferences. However, your preference itself wouldn't change. And we have small finite MDPs, which allow for tractable planning. Maybe they are finite, so we could actually maybe solve them using value iteration, so they are tractable. However, they are not nearly as tractable as bandits. But actually, we can also say a few things about exploration here too. So the question is, how can an exploration problem be made tractable in the end? In multi-armed bandits, we have the exploration problem that can actually be formalized as a partially observable Markov decision process identification. So we actually don't know everything about the world we need to know. And if we can actually formalize this also as a partially observable Markov decision process. And actually, if we do this and we learn a lot about the partially observable Markov decision process, then policy learning is easy, even in the partially observable Markov decision process. We have small and finite MDPs. we can actually frame this one as an exploration problem, as a with a Bayesian model identification process. So we actually maintain a sort of distribution over beliefs over the states we have, and if this is limited, we can actually form the posterior and solve this, and then we can actually also reason about the value of information that we have and where we actually need more information about the environment. And we have large and infinite MDPs, such as things like Montezuma's Revenge or complex robotics tasks, where their optimal methods just don't work here, and we need to take inspiration from the other works in order to actually work well on those problems. And of course, also we use a lot of hacks that we usually are familiar with when we do deep reinforcement learning. So we will talk about large and infinite MDPs a lot in the second part of the lecture, when we actually discussed all the classical exploration strategies that mostly apply to the first two settings. Okay, so I said a lot of times, I talked about multi-armed bandits. The question is, what is a multi-armed bandit? A multi-armed bandit is a classic problem that has been used a lot actually to study the exploration versus exploitation dilemma. The word actually stems from such guys. So this is actually what you see is a one-armed bandit in here. You have an arm on the right side and you can play a game, and given some probability that's encoded in the machine, you get a reward or you get no reward. And so actually, and now imagine that you're in a casino with multiple such one-armed bandit slot machines, and each of them is configured with an unknown reward probability that you just don't know. And this is then a multi-armed bandit problem. And so actually look at this. So the question is now, this is the different slot machines that you see in the casino, and the question is, what you don't know, but what you don't know see, but what is encoded in the machine, this is the reward probability of actually getting a reward if you play this bandit. And now, under the assumption of an infinite number of trials, so that you can play forever, what is the best strategy actually to achieve the highest long-term rewards? And this is actually the basic formalism to actually study the problem of exploitation versus exploration, because you actually want to find out which machine actually gives you the highest reward. However, you want also to actually get some estimate of how big the probability of getting a reward is from all the machines without exploring them too often, because you actually want to maximize your long-term reward. Of course, there's also settings with limited number of trials, or even less trials than you have available slot machines, but we actually don't discuss this in here. The question is now, how can we actually make a selection on playing which of the arms in the bandit to actually yield the longest, the best exploration strategy? And what you see in here is also something a little picky in the definition. So this goal now includes the training steps in our agents actually, and we want to minimize the training steps in a sense. So we want to actually minimize the training steps in order to actually get out the strategy that we need to get the longest, the basic long-term reward, which is something that we usually do not focus so much when we talk about RL. Okay, to actually give a solution for that. So a naive solution to do this would actually be, you play each machines for many rounds, so actually going to infinity. And if you do this, actually you can estimate the true reward probability of each of the machines due to the law of large numbers, so you can just average it. And then you can act greedily with respect to the uncovered probabilities. However, of course, this is not only very time consuming, it's also wasting a lot of money. And usually you cannot really apply the setting that you have infinite samples that you can take from the environment. And this is actually why we want to why we want to come up with a strategy that minimizes the training steps until we can really be sure to have a decent estimate of the winning probabilities. Okay, to formally define a multi-armed bandit, so we define a Bernoulli multi-armed bandit, and it can be described as a simple tuple containing actions and rewards, where we have actually n machines, and all of the machines have associated reward probabilities, theta 1 to theta n, and at each time step t, we take an action AT on a single slot machine, and we receive a reward RT from using this. So our action space is actually a set of actions. In other words, there's arms. So we can either pull the arm of bandit 1, 2, 3 until n. And each action actually refers to the interaction with a single slot machine. And the true value of the action A is actually the expected reward. So actually the true state action, or the action value actually for each of the action, is actually the expected reward undertaking the action, which is actually the winning probability, the reward probability theta of this action. And actually, if some more definition, if the action AT at time step t is on the eth machine, then Q of AT is in the end theta I, meaning that that we actually can assume that the Q function will be the winning probability. However, note that the value function at this point is unknown. Okay, and on the other side we have R. R, as usually, is a reward function, meaning that we observe a reward R in a stochastic fashion. So at each time step t, we receive a reward RT, which is actually the reward of the given AT into the reward function, and it draws from a probability distribution over the action. And in this case, actually, as we have a Bernoulli multi-armed bandit, it returns a reward of 1 with a probability of theta I, which is QAT, or 0 with a probability 1 minus theta I. And also in this case, the distribution P R given A is fixed, but it's unknown. So, and the question now is, what do we want to do? We want to maximize the cumulative reward, which is actually over our time steps, all the rewards we actually get. We sum it up, and actually this is what we want to optimize or maximize. And as usual, PAR is unknown, but we still want to estimate the Q function. So this is actually a setting that we're quite familiar with. And also one note at this point, basically this is still an MDP. However, there is no states at this point involved, or you could just say that we always are in the same state as 0 and we will never change the state. This makes it actually a fully defined MDP in this case. And yeah, so actually one more thing to mention, if we make the interpretation of the partially observable Markov decision process, we could actually say that the associated probabilities are the state that we actually don't know. So we actually get only partial information on the state. And we can actually, what we could do, or how we could interpret the problem also, we could also, through our process, maintain a belief state over our current estimation of such probabilities. And then we could actually come up with a Bayesian optimal bandit that selects, actually through estimating the posteriors, to estimate the action that actually increases the belief over our states. However, if we have large set of reward probabilities, this probability distribution over the states actually becomes really huge, and the problem becomes intractable to really do this in practice. Yeah, so now the question is, how do we actually, so actually if we have some exploration strategy that tries to actually take these arms and actually tries to uncover the reward probabilities, how can we actually measure the goodness of such an exploration algorithm? And in order to actually measure the goodness of such an exploration algorithm, we come up with the formulation of a so-called regret, which is actually the difference between the optimal policy at time step t and our suboptimally used action AT that we actually took at this place. So let's formalize this a little bit. So the regret is something that we will resort a lot to. So still our goal is to maximize the cumulative reward. And let's first define what is the optimal reward probability pi theta of the optimal action A theta. So pi A star, theta star and A star. So theta star, this is actually the optimal reward probability that we can get. So this is the maximum we can get. So if we always play the best machine, this is what we can expect from our MDP if we play like optimally. And this is actually what we can get. And theta star is nothing else than QA star, which is actually the maximum Q value over all A's. And this is actually equal to the maximum theta in this case. And this is also, like in expectation, the maximum we can get if we take actually all the actions from this state. So this is actually the best we can achieve if we have like t equals 20, if we have 20 steps. This is actually what we can get, 20 times the best reward probability. And now actually the question is, how can we actually reason about the exploration-exploitation trade-off? And we can actually use the kind of regret as something like a one-step opportunity loss. So the question is, now we take an action, so maybe let's uncover this. So we define a loss function, and the loss function is the total regret that we might have by not selecting the optimal action up to some time step t. So like imagine that we run in t time steps, so capital T time steps, and the regret if we do this according to some exploration strategies is simply the difference of, or like for each of these time steps, the difference between the reward probability of the best action over the reward probability or the Q estimate of the or the reward probability of the action that we actually took in this state. So actually the difference between what we should have been doing in order to get a maximum reward out of it and what we did actually. So we can also like giving you an analog to the thinking. So in hindsight, you might regretting taking the tube rather than going by a bicycle. However, it might you might have also regretted taking the bus even more. So like there's an opportunity loss that you don't know, and you can actually say how much did you actually regret the action that you actually took. So this is the question that the regret loss function actually answers. And it turns out if you do it like this, and I mean the probabilities of so the uncovered probabilities doesn't change, you can actually reformulate this and say, okay, this is actually the same as for all of the action, the number of times you select a certain action times the opportunity loss that you actually observe through this action. And this is actually what you want to minimize. So you want to actually minimize the number of times you took an action that actually has a large action regret. So this is actually what you want, and you want to have you want to maximize the counter for actions that have a low per action regret. So this is actually what you want to do. And however, the question is now, where do we actually have the uncovered probabilities from? And this is actually nice because for small multi-arm bandits problems, we can actually define such probabilities, which also means that we can come up with algorithms and we can benchmark them in terms of their regret. Okay, to actually formalize or sum up the notion of regret a little bit more. So if we knew the optimal action that gives us the best regret, then maximizing the number of cumulative rewards is actually the same problem as minimizing the total regret. However, the agent cannot observe or sample the real regret directly, but we can actually analyze different exploration strategies with this information. Two further notes. So the sum for the total regret actually extends beyond single step episodes. So we actually not using episodes in here. So we actually use training time steps. This is actually what we do in this. So we unsettle the problem of breaking something down into episodes. And we actually always consider the lifetime of learning rather than having a reward per episode or something like this. This is just what I said in the beginning. A good exploration algorithm actually ensures a small visitation count for actions that have a large action regret. However, the action regrets are unknown. Okay, so from here we can actually derive three different strategies that we can use in Bandits. So the first one is we can do no exploration at all. So this is very naive and it's usually a very bad one to do, and we have also seen this in practice. We can do exploration at random. This is actually what we did with Epsilon Greedy, and which we also cover or actually benchmark in the next lecture. However, what we actually want to do and what we will be doing is we can do a smart exploration with a preference to explore actions on which we actually have a high uncertainty in knowing what their reward probability associated with it actually is. And this is actually what we will be covering in the upcoming lecture video.